The universe had billions of years before us, enough time for civilizations to rise, expand, and fill the galaxy many times over. By pure mathematics, they should already be here. Their signals should be everywhere. But instead, we see nothing. Absolute silence. Today, we uncover the paradox behind that silence and why every possible answer points to something deeply unsettling about our own future. Now let's begin. Right now, according to nothing more exotic than basic arithmetic, at least one alien civilization should have already reached every corner of this galaxy. Their signals should be flooding our radio telescopes. Their probes should be drifting through our solar system. Their megastructures should be rewriting the infrared map of the night sky. Instead, nothing. Not a whisper. Not a blip. Not a single confirmed signal in over 60 years of searching. That is not a mystery. That is a contradiction. And the gap between what the math demands and what reality delivers is the most unsettling silence in the history of human thought. Here is the arithmetic that makes it unavoidable. The universe is 13.8 billion years old. Earth is 4.5 billion years old. That means the universe existed for 9.3 billion years before this planet even formed. 9.3 billion years of stars igniting planets, cooling chemistry, assembling itself in the dark before a single grain of sand settled on what would eventually become the ground beneath your feet. Now put that number into human terms. Our entire civilization, from the first cities in Mesopotamia to the device you are reading this on, is roughly 10,000 years old. Against 9.3 billion years, that is not even a rounding error. It is essentially zero. So, here is the question that should stop you cold. What if something else started just a little earlier? Not millions of years earlier, not billions, just 2 million years less time than our own genus Homo has walked this planet. If any civilization had appeared 2 million years before us and expanded outward at just 1% of the speed of light, no warp drives, no exotic physics, nothing that violates any known law of nature, they would have reached every star system in the Milky Way, long before the first dinosaur ever set foot on Earth. They would have had billions of years to settle, to build, to leave traces so massive and so permanent that they would be impossible to miss. The Milky Way has 400 billion stars. More than 100 billion planets orbit them. For decades, astronomers debated whether planets were common or rare. That debate is finished. Every major telescope survey of the last 20 years has confirmed the same answer. Planets are not the exception. They are the rule. On average, every single star in this galaxy has at least one world in orbit around it. Some have many more. By any honest application of probability, the conclusion is inescapable. Somewhere in this galaxy, something should have developed intelligence before us. And if it did, the evidence should be everywhere, unmistakable, overwhelming, impossible to overlook. Instead, the Milky Way is silent. Completely, perfectly, disturbingly silent. This is not for lack of effort on our part. The search for extraterrestrial intelligence has been listening continuously for more than 60 years. Researchers have swept through millions of radio frequencies. They have pointed instruments at hundreds of thousands of individual stars. They have built algorithms sensitive enough to detect signals of almost unimaginable faintness across interstellar distances. The technology has improved by orders of magnitude since the search began. The answer has not changed once. Not one confirmed artificial signal. Not one structure that defies natural explanation. Not one anomaly that survives scientific scrutiny as evidence of technology. Zero. This is where most people make a comfortable mistake. They file this under interesting open questions, the kind of puzzle science will eventually resolve, like dark matter or the origin of consciousness. But that framing dissolves the moment you look at it directly. This is not a gap in knowledge. It is a direct collision between two things that cannot both be true at the same time. Either the math is catastrophically wrong about how life and intelligence arise, or something is systematically stopping civilizations from leaving a mark on the universe. Both options are deeply uncomfortable. Neither can be dismissed. And here is the part that makes this personal. Every serious explanation for why the universe is silent carries a direct implication for us. Not for some abstract future version of humanity living 10,000 years from now. For this civilization, for the next 100 years on this planet. The answer to why the sky is quiet is inseparable from the question of whether we survive long enough to find it. Some of those answers are unsettling, some are worse than that, and none of them allow us to simply look away. The universe is silent, the math says it cannot be, and in the space between those two facts lies the most important question our species has ever failed to answer. If the universe is old enough, large enough, and filled with enough worlds to make life almost inevitable by the numbers, why is the sky completely, totally, perfectly quiet? To understand why that silence is so disturbing, we first need to understand just how airtight the case for a crowded universe once seemed, and why the scientists who built that case were not being naive. They were being rigorous. The logic was sound, the data was real, and that is exactly what makes the silence so hard to explain. In November of 1961, in a small conference room in Green Bank, West Virginia, a group of scientists did something that had never been attempted in the entire history of human inquiry. They tried to count other civilizations, not estimate, not philosophize, count using real variables, real data, and real mathematical logic. The man who made it possible was Frank Drake, a young radio astronomer who had already spent time pointing telescopes at nearby stars and listening for anything unusual. That morning, Drake picked up a piece of chalk and wrote a sequence of variables on a blackboard that would be debated, expanded, and cited for the next 6 decades. The equation was not designed to produce a single, precise answer. It was designed to do something more valuable, to force a rigorous, structured conversation. It broke the enormous question of whether intelligent life exists elsewhere into a chain of smaller, harder questions. How many new stars form in the Milky Way each year? Of those stars, how many have planets? Of those planets, how many sit in the zone where liquid water could exist on a surface? On those worlds, how often does life actually emerge? When life emerges, how often does it evolve into something intelligent? When intelligence appears, how often does it build technology capable of sending signals across interstellar space? And finally, the variable that would later prove the most haunting of all, how long does such a civilization actually survive before it goes quiet? When Drake and his colleagues worked through each factor carefully, using estimates that were cautious but not pessimistic, the numbers stacked up in a direction that felt genuinely electrifying. The conclusion was difficult to avoid. The Milky Way should at any given moment contain somewhere between thousands and millions of civilizations capable of communication. The galaxy should be alive with signals. The night sky should be saturated with the electromagnetic fingerprints of other minds reaching across the void. Then, in the decades that followed, the observational data arrived, and instead of weakening that conclusion, it strengthened it repeatedly. From multiple independent directions, in 2009, NASA launched the Kepler Space Telescope with a single focused mission: stare at a fixed patch of sky and watch for the infinitesimal dimming of starlight that signals a planet crossing in front of its sun. Over 9 years of continuous observation, Kepler confirmed more than 2,600 planets beyond our solar system. More critically, it provided the statistical foundation to estimate how common planets truly are across the galaxy. The answer was staggering: tens of billions of roughly Earth-sized planets orbit within the habitable zones of their stars in the Milky Way alone, not across the entire observable universe. Just in our galaxy, tens of billions of worlds where liquid water could exist on a surface, where the basic conditions for chemistry are met, where the stage is set. Then the search moved closer to home, and what researchers found made the argument even harder to dismiss. Europa is one of Jupiter's moons, a frozen sphere slightly smaller than our own moon. For a long time it looked like a dead, featureless ball of ice. Then scientists analysed the pattern of fractures on its surface, measured the subtle shifts in its crust over time, and modelled the tidal forces Jupiter exerts on its interior. The conclusion was remarkable. Beneath Europa's icy shell lies a global ocean of liquid salt water, not a thin layer. A full, deep ocean containing more liquid water than all of Earth's oceans combined, kept liquid not by a nearby star, but by the gravitational friction of Jupiter's immense pull churning the moon's interior for billions of years. On Earth, we know that life clusters around hydrothermal vents at the bottom of our oceans in complete darkness, under crushing pressure, entirely independent of sunlight. Europa has had the same conditions for longer than complex life has existed on this planet. Enceladus, a small moon of Saturn, made the case even more dramatic. In 2005, the Cassini spacecraft detected something extraordinary: enormous geysers of water vapor erupting from cracks near the moon's south pole, shooting material hundreds of kilometers into open space. Cassini flew directly through these plumes and analyzed what it found: water, organic compounds, silica particles indicating hot liquid water interacting with rock on the seafloor below, and molecular hydrogen almost certainly produced by hydrothermal reactions, the same chemistry that powers the deep-sea vents on Earth, where entire ecosystems flourish without a single photon of sunlight. Enceladus is actively venting right now the precise chemical signatures of an environment that could sustain life. It is not a relic. It is ongoing. Beyond our solar system, the picture continued to build. Amino acids, the molecular building blocks from which all known life assembles its proteins, have been detected in meteorites that fell to Earth, in comets analyzed by spacecraft, and in the cold molecular clouds drifting between stars. The chemistry of life is not a bizarre local accident unique to one pale blue dot. It appears spontaneously wherever conditions permit. The same carbon bonds, the same nitrogen chemistry, the same organic reactions that built the first cells on Earth emerge in interstellar space, in the hearts of comets, in the debris fields left by dying stars. Life's raw materials are not scarce. They are woven into the fabric of the universe itself. Every piece of data pointed the same direction. Planets are everywhere. Liquid water exists throughout our own solar system. The chemical ingredients of biology are universal. The conditions for life are not exceptional, they are ordinary. Carl Sagan, who spent much of his career thinking carefully about exactly this question, stated it plainly: if we are the only intelligence in a universe this vast, then an almost incomprehensible amount of space is going to waste. He was not being poetic. He was being logical. The reasoning was sound. The observations were real. Every new telescope, every new mission, every new discovery seemed to add another layer of confirmation onto a case that already felt overwhelming. A universe this old, this large, and this chemically generous should be filled with life. The galaxy should be crowded with civilizations. The signals should be everywhere. The telescopes listened, the algorithms searched, the dishes swept across the sky frequency by frequency, star by star, year after year, and heard absolutely nothing. If every independent line of evidence, the abundance of planets, the universality of organic chemistry, the discovery of liquid water across our own solar system, all points toward a universe that simply cannot be empty, why is it so completely, so perfectly, so inexplicably quiet? That collision between expectation and reality has an official name, and it was born not in a laboratory or an observatory, but from a single offhand remark at a lunch table, spoken by one of the most formidable scientific minds of the 20th century. Not every world-changing idea arrives with fanfare. Some arrive at a lunch table between bites of food, spoken by a man who was simply thinking out loud. The year was 1950. The place was Los Alamos National Laboratory in New Mexico, the same facility where the atomic bomb had been designed just a few years earlier. Enrico Fermi was eating lunch with colleagues when the conversation drifted, as it sometimes did in those post-war years, toward the question of unidentified flying objects. The topic was light. The mood was relaxed. Then Fermi went quiet for a moment, turned something over in his head, and asked a question so simple it almost sounded naive. "Where is everybody?" his colleagues laughed. Then they moved on to other topics. Nobody at that table understood what had just happened. But that question, 4 words utterly plain, requiring no mathematics to state, has never been satisfactorily answered in the 75 years since Fermi asked it. Every serious attempt to resolve it has either deepened the mystery or produced an answer more disturbing than the question itself. To understand why, you need to understand who Fermi was. He was not a man given to sloppy thinking. Enrico Fermi is the only physicist in the 20th century to have achieved world-class mastery of both theoretical and experimental physics simultaneously, 2 disciplines that demand such different modes of thinking that virtually no one manages both at the highest level. He designed and built the world's first nuclear reactor beneath a squash court at the University of Chicago in 1942. He was famous among his peers for a particular skill, the ability to arrive at startlingly accurate estimates of complex quantities using nothing but logical reasoning known today as Fermi estimation. When Fermi asked a question, it was not idle curiosity. It was the output of a calculation already running in the background. So when he asked, "Where is everybody?" he had already done the arithmetic. Here is what that arithmetic looks like, stripped of any formulas. The Milky Way is roughly 10 billion years old. It contains hundreds of billions of stars. If only 1/10,000th of 1% of those stars, a vanishingly small fraction, hosted a planet where a technologically capable civilization arose that still produces hundreds of thousands of civilizations across the galaxy. Hundreds of thousands. Now consider what any one of those civilizations could do with enough time. If a civilization develops spacecraft capable of traveling at even a few percent of the speed of light, well within the reach of plausible engineering, requiring no physics beyond what we already know, and pauses at each new star system long, enough to establish a colony before sending new ships onward, the mathematics of expansion are relentless. The entire Milky Way, all 100,000 light-years of it, gets covered in somewhere between 2 million and 10 million years. 10 million years sounds enormous until you hold it against the age of the galaxy. 10 billion years. 10 million years is just 1/10 of 1% of that. If any civilization had started this process, even 1/10 of 1% earlier than us earlier, by a margin that is essentially noise on a cosmic timescale, they would have finished colonizing the entire galaxy before our solar system even existed. Their presence should be everywhere, unmistakable, permanent. And this is what makes Fermi's question so uncomfortable. It is not a question about whether we have looked hard enough. It is a question about why there is nothing to find. This is where the Fermi paradox does something unusual in the history of science. Most unsolved problems involve missing data. We simply do not have enough information yet. The Fermi paradox is different. The data we have is complete, consistent, and deeply negative. It does not matter which direction we look. It does not matter which frequency range we search, or which type of signal we try to detect. The absence is total and uniform across every instrument, every method, every decade of searching. That kind of systematic, consistent negative result is itself a form of data. The silence is not a gap in our knowledge. The silence is the finding. And here is the distinction that matters most, because it is the one most commonly misunderstood. The Fermi paradox does not claim there is no life beyond Earth. It does not assert as a conclusion that we are alone. What it asserts is far more precise and far more troubling if advanced civilizations exist or have existed. The observable evidence of their presence should be inescapable, and it is not there. The paradox is not about the absence of life. It is about the absence of evidence from life that by all logical expectations should be impossible to hide. Which brings us naturally to the only escape route available. Something is wrong with the expectations. Either civilizations are far rarer than the math suggests, or they do not last long enough to spread, or they choose not to, or they are present but invisible to us, for reasons we have not yet understood, and this is the possibility that tends to keep researchers quiet at the end of long conference. Days, something happens to all of them before they get the chance. The birthday party analogy is almost too accurate to be funny. You spend weeks preparing. You send invitations to the entire neighborhood. You cook enough food for 100 people, hang the decorations, and wait by the door all evening. Nobody comes. Not a single knock. Not one. And the unsettling realization as the night wears on is that the most likely explanation is not that everyone was busy, it is that something happened to everyone before they could arrive. That is the Fermi paradox. That is the silence, and it is not a comfortable thing to sit with. What do you think actually happened to them? The civilizations that should have been here long before us. Scientists have not been content to simply live with the discomfort. They have proposed dozens of explanations, and some of those explanations are not just unsettling in the abstract. They carry direct implications for the fate of this civilization on this planet in this century. There is no shortage of proposed solutions to the Fermi paradox. Researchers have generated dozens of them over the past 7 decades. But strip away the technical language, and what you are left with is a small number of distinct scenarios, each one a different version of reality, each one frightening for reasons that are entirely its own. Scenario 1: The Rare Earth. In 2000, Peter Ward and Joe Kirschvink published a systematic argument that challenged one of the most comfortable assumptions in astrobiology. The assumption was, this Earth is a typical planet. Liquid water, stable climate, complex life. These things should arise wherever the basic conditions are met. Ward and Kirschvink argued the opposite. Earth, they contended, is not typical. It is the product of an extraordinary series of coincidences, each individually unlikely, that somehow all occurred simultaneously on the same world. Start with the Moon. Earth's moon is absurdly large relative to its host planet, far larger proportionally than any other moon in the solar system, except for Pluto's companion Charon. That size matters enormously. The moon's gravitational influence stabilizes the tilt of Earth's rotational axis, keeping it within a relatively narrow range over millions of years. Without that stabilization, Earth's axial tilt would wander chaotically, swinging between extremes that would produce climate shifts so violent and so rapid that complex life could never gain a stable foothold. The moon is not a scenic feature. It is a climate regulator. Then there is Jupiter. The solar system's largest planet sits in an orbit that intercepts a vast number of comets and asteroids that would otherwise be flung toward the inner planets. Jupiter acts as a gravitational shield, absorbing or deflecting debris that, if it reached Earth at the rate it otherwise would produce mass extinction events so frequently that evolution would be repeatedly reset before complexity could accumulate. Without Jupiter in its current position, Earth gets hit far more often. Complex life probably never makes it out of the ocean. Then there is Earth's position within the galaxy itself. We orbit at a comfortable distance from the galactic center, far enough to avoid the punishing radiation environment that sterilizes the inner regions of the Milky Way, but not so far out toward the edge that the raw materials for building rocky planets become scarce. This band of habitability within the galaxy, sometimes called the galactic habitable zone, is narrower than most people assume. And then there is Earth's magnetic field, generated by its liquid iron core, which deflects the solar wind and prevents it from stripping away the atmosphere, exactly what happened to Mars, which lost its magnetic field billions of years ago, and is now a desiccated shell of a world with almost no air left. Any one of these factors missing or slightly altered, and Earth becomes uninhabitable for complex life. The terrifying implication of the rare Earth hypothesis is not just that we got lucky. It is that we may have gotten lucky in so many independent ways simultaneously that the combination is effectively unique. We are not typical. We are an accident, and accidents by definition do not repeat reliably. Scenario 2. The Great Filter is already behind us. In 1998, economist Robin Hanson published a paper that reframed the entire conversation. If the universe is filled with potentially habitable worlds but appears devoid of advanced civilizations, then somewhere in the chain of steps, from simple chemistry to spacefaring intelligence, there must be a step that is almost impossible to cross. Hanson called this the Great Filter. The crucial question is where in that chain the filter sits. The most hopeful possibility, and it is a genuine hope, not wishful thinking, is that the filter lies behind us, that we have already crossed it. The strongest candidate is the transition from simple prokaryotic cells, which are cells without a nucleus, to complex eukaryotic cells, which have a nucleus and internal structures. On Earth, this transition took approximately 2 billion years to occur, and it happened exactly once. Not several times independently. Once. The mechanism that produced it, one cell engulfing another and forming a stable symbiotic relationship rather than simply digesting it, appears to be extraordinarily improbable. If this step is the Great Filter, then simple microbial life may be common throughout the universe, but complex life is vanishingly rare, and we, having already made that crossing, can breathe a carefully qualified sigh of relief. The conditional part matters. This is only good news if we do not find complex life elsewhere. The moment we do, the filter must lie somewhere else. Scenario 3. The Great Filter is still ahead. This is the scenario nobody wants to be right. If complex life is actually not that rare, if intelligence arises with some regularity throughout the galaxy, but the universe is still silent, then the filter is not behind us. It is waiting. Somewhere between where we stand now and the point of becoming a true spacefaring civilization, there is a wall that every technological species hits, and none of them in the entire history of the Milky Way have gotten through it. The mechanism does not need to be exotic. A civilization that develops the ability to engineer pathogens faster than it develops the wisdom to govern that ability. An artificial intelligence that optimizes for goals misaligned with the survival of its creators. Access to energies capable of planetary-scale destruction before the institutional structures exist to prevent their use. These are not science fiction premises. They are engineering problems that follow naturally from the same trajectory of technological development we are currently on. The truly disturbing part is not that such a wall might exist, it is that we are, by any honest assessment, standing right in front of where it would be. The same century in which we learn to split the atom is the century in which we are building artificial general intelligence and engineering novel biological agents. We are in exactly the phase where the filter, if it exists, would be located. Scenario 4. The zoo hypothesis. Perhaps they know we are here. Perhaps they have known for a long time. And perhaps for reasons that are entirely opaque to us, policy ethics protocol, or something we do not have a concept for, they have chosen not to make contact. The zoo hypothesis proposes that advanced civilizations observe less developed ones without intervening much, as conservation biologists monitor wildlife without disrupting it. The silence is not absence, it is restraint. Deliberate, maintained, enforced restraint. The unsettling implication is not the possibility of being watched. It is the repositioning it implies. In this scenario, we are not the observers, we are the observed. We are not the ones asking whether anyone else is out there. We are the specimen in someone else's study. Scenario 5. The dark forest. This one will be examined in full later. For now, the premise is enough. The silence is not absence, and it is not restraint. It is survival strategy. Every civilization in the galaxy has learned the same lesson, the same cold, logical, unavoidable lesson. And that lesson is do not make a sound. The universe is a dark forest, and every civilization in it is holding its breath. Which one frightens you more? A filter waiting somewhere ahead of us that no civilization has ever crossed, or the possibility that something already knows exactly where we are and is choosing for now to say nothing in the middle of all? To these hypotheses, all this theory and calculation and dread, something real happened. A single signal, 72 seconds of data that nearly 50 years later still has no universally accepted explanation. Nobody was watching when it arrived. That is the first thing to understand. On the night of August the 15th, 1977, at 11:16 in the evening, the Big Ear radio telescope at Ohio State University was doing what it always did, sweeping methodically across the sky, collecting data, recording everything onto a continuous printout. No astronomer was sitting at the controls. No one was monitoring the feed in real time. The telescope was alone in the dark, listening on behalf of a species that was mostly asleep. Whatever came through that night came through unwitnessed. 3 days later, a volunteer astronomer named Jerry Amon sat down with the printout to do what he regularly did. Review the data by column, looking for anything that stood out from the background noise of the cosmos. It was painstaking work. The numbers and letters scrolled past in predictable, unremarkable patterns. The universe, as usual, was saying nothing. And then Amon stopped. To understand what he saw, you need to understand how Big Ear encoded its data. Signal intensity was represented on a scale that ran from 1 through 9, then continued through the letters of the alphabet. A representing 10, B representing 11, and so on upward. The ambient background noise of the universe, the natural electromagnetic hiss of deep space, typically registered between 1 and 3 on that scale. A signal reaching 4 or 5 was notable. Anything higher was exceptional. In years of continuous observation, values that high were essentially unheard of. The sequence Amon found in the printout read 6EQUJ5. The peak, the letter U, represented an intensity of 30 times above the background noise of the surrounding sky. 30 times. The signal had risen steadily, reached that extraordinary peak, held briefly, and then faded back down in a smooth, symmetrical curve before disappearing entirely. From first detection to last 72 seconds, Amon circled the sequence in red pen. In the margin beside it, he wrote a single word: "Wow." The name stuck. Nearly 50 years later, it is still the only name this signal has. What made the wow signal genuinely extraordinary was not just its intensity. It was the combination of technical characteristics that, taken together, matched almost perfectly the theoretical profile of what an artificial extraterrestrial transmission should look like, according to criteria that SETI researchers had established years before the signal arrived. The frequency was the first remarkable detail. The signal was detected at 1420 MHz, which corresponds precisely to the natural emission frequency of neutral hydrogen, the most abundant element in the universe. This frequency had long been proposed by SETI theorists as the most logical channel for interstellar communication. The reasoning was straightforward. Any civilization that understood basic physics would know this frequency. It requires no shared language, no prior contact, no cultural common ground. It is written into the structure of matter itself. If you wanted to broadcast a signal that any technologically capable receiver could find, this is where you would broadcast it. The bandwidth was the second critical detail. The WOW signal was extraordinarily narrow, far narrower than any known natural astrophysical source. Natural radio emissions from cosmic objects tend to spread across a range of frequencies. Artificially generated signals, by contrast, are typically concentrated into a very tight frequency range, because that is simply how transmitters work. The narrowness of the WOW signal's bandwidth was not consistent with any natural phenomenon that radio astronomers recognized. It was consistent with a transmitter. The directionality was the third detail. The signal came from the direction of the constellation Sagittarius, from a region of sky that contained no known celestial object of particular note. No pulsar, no quasar, no magnetar, nothing that could account for an emission of that character and intensity. And the shape of the signal itself was the fourth. As Earth rotated during those 72 seconds, the source tracked across the telescope's field of view in precisely the pattern that would be expected from a fixed point source located far beyond our solar system. The rise and fall of the signal intensity followed the theoretical curve almost exactly. It behaved in every measurable respect exactly as an extraterrestrial transmission should behave. The search that followed was exhaustive and ultimately empty. Big Ear returned to that region of sky more than 50 times over the years that followed. Nothing. Other telescopes far more sensitive than Big Ear swept the same coordinates repeatedly across subsequent decades. Nothing. The signal that had appeared once with perfect clarity for precisely 72 seconds never came again. In 2016, an astronomer named Antonio Paris proposed a natural explanation. Two comets designated 266 P-stroke Christensen and P-stroke 2008. Y2 had been in the vicinity of that region of sky in August of 1977, Paris argued. Comets carry hydrogen, and hydrogen emits at exactly the frequency the WOW signal used. Perhaps the signal was simply hydrogen emission from a comet's coma, rather than anything artificial. The scientific community examined the hypothesis carefully and found it wanting. The velocity signatures of comets produce a characteristic frequency drift that was not present in the WOW signal. The intensity was difficult to reconcile with what a comet's hydrogen cloud should produce at that distance. Independent researchers ran the numbers and remained unconvinced. The comet explanation has not been falsified, but it has not been accepted either. The debate continues. What this means nearly 5 decades after that night in Ohio is that the most significant candidate signal in the entire history of SETI remains exactly what it was when Eamon circled it in red pen, unexplained. And that is the truly haunting part. Not the question of whether it was artificial, not even the question of where it came from. The haunting part is that we do not know, and after 50 years of trying with every tool modern astronomy can bring to bear, we still do not know. The universe handed us 72 seconds of something remarkable and then took it back and has offered nothing since. If it was artificial, if something somewhere in the direction of Sagittarius aimed a transmission at this small planet on that specific night, then they sent it exactly once. One transmission, one window, and we were not even awake when it arrived. We caught it by accident 3 days late on a paper printout read by a man with a red pen. The WOW signal does not prove that extraterrestrial intelligence exists. What it proves is something subtler and in some ways more unsettling, that the universe is entirely capable of producing phenomena that match every criterion we established for an artificial signal, and then offering us no way to confirm or deny what we found. It passed our own test, and then it disappeared. If the wow signal was real, if something sent that transmission once and only once directly toward Earth, would you want us to answer it? Of all the things we do not yet know, there is one thing the science makes uncomfortably clear. If we discovered extraterrestrial life tomorrow, the correct response would not be celebration. It would be fear. And the reason for that is more logical and more disturbing than you might expect. Imagine waking up tomorrow to this headline: NASA confirms microbial life discovered on Mars. Take a moment to feel the instinctive response, the elation, the vindication, the sense that humanity has just crossed one of the most significant thresholds in its entire history. Proof at last that we are not alone. Scientists would weep. Celebrations would erupt across every city on Earth. It would be, by almost any measure, the greatest scientific announcement ever made. Now, consider the argument made by Nick Bostrom, philosopher at Oxford University, and one of the most rigorous thinkers working on existential risk. Bostrom has argued in careful and systematic terms that the discovery of even the simplest life beyond Earth, as a bacterium, an archaeon, a single-celled organism of any kind, might constitute the worst news in the history of our species. Not metaphorically, not as a provocative exaggeration, literally the worst news. And the logic behind that claim is airtight. Follow the chain of reasoning step by step. If simple life, microbial, primitive, single-celled, managed to emerge on Mars, a planet that is cold, largely airless, bombarded by radiation, and has been geologically dead for billions of years, then the conclusion is nearly inescapable. Origin of life is not a rare accident. It is something chemistry does when given even marginal opportunities. If life can start on Mars, it can start almost anywhere the basic ingredients are present. And we already know those ingredients are scattered throughout the universe. The implication is that simple life is probably common, perhaps extraordinarily common across the cosmos. But the universe is still silent. No signals, no megastructures, no evidence of anyone out there who has progressed beyond the microbial stage to build technology, transmit messages, or leave any mark on the galaxy. If simple life is common, but technological civilization is absent, there is only one logical conclusion available: somewhere between the origin of life and the development of spacefaring intelligence, there is a step that almost nothing survives. A wall, a filter so difficult to cross that, across the entire history of the Milky Way in billions of years of cosmic time, nothing, or almost nothing, has made it through. The critical question is where that filter sits relative to us. If we find life on Mars, the filter is almost certainly not behind us, because if life arising is easy enough to happen independently on two neighboring planets in the same solar system, then that step is not the filter. The filter must lie further along the chain, which means it lies ahead, which means we have not crossed it yet, which means every civilization that has ever existed has hit that wall and failed, and we are next in line. Each additional world where simple life is found tightens this logic further. Every positive result in the search for basic biology elsewhere is another data point confirming that life's origin is not the bottleneck, and therefore that the bottleneck must be somewhere between where we are now and where we would need to be to survive as a spacefaring species. This is why some researchers working in astrobiology approach their own field's central goal with a quiet, private ambivalence that is almost never discussed publicly. The rover Perseverance is drilling cores from ancient lakebeds on Mars right now, analysing sediments that were laid down billions of years ago when liquid water still flowed on the surface. The explicit mission objective is to search for biosignatures, chemical or structural evidence of past life. The science is impeccable. The mission is extraordinary. And there are scientists, serious ones, who are genuinely hoping it finds nothing. Not because they lack curiosity, because they understand the implication of a positive result. The stakes escalate further when you consider Europa Clipper, launched in 2024, currently en route to Jupiter's moon Europa. Its instruments will analyze the chemistry of that global subsurface ocean the same ocean that has existed in darkness for billions of years, the same ocean that contains more liquid water than all of Earth's combined. If life exists in Europa's ocean, it arose independently from any life on Earth in the same solar system in conditions radically different from ours. That would not merely confirm that life is common. It would confirm that life is almost inevitable wherever liquid water and chemistry meet. And if life is almost inevitable but the galaxy is still silent, then the filter ahead of us is not just real, it is catastrophic. It is something that stops virtually everything, and we would have no idea what it is or how close we are to it. The inverse logic deserves equal attention because it is genuinely the more hopeful scenario, even though it feels less satisfying. If every search returns empty, if Mars has no fossils, Europa has no biology, Enceladus has nothing alive in its plumes, then the filter might truly be behind us. The origin of life itself might be extraordinarily rare. We might have beaten odds so long that complex life is essentially unique. That is a lonely conclusion, but it is a survivable one. Empty skies above and empty petri dishes below would be paradoxically the best possible outcome for our long-term future. The universe has handed us a situation in which the most exciting scientific discovery imaginable is also potentially a death sentence written in biological ink, and in which the most discouraging null result is quietly, privately the result many thoughtful people are hoping for. Would you want to know the truth, even if the truth turned out to be the worst possible news? But suppose the filter is already behind us. Suppose we are among the rare ones who made it through. That does not mean the path ahead is open, because there is still the question of where we actually stand in the civilization of the cosmos. And the answer to that question is not comforting. In 1964, a Soviet astrophysicist named Nikolai Kardashev proposed a way of thinking about civilizations that cut through every variable of culture, biology, language, and history, and reduced the question to a single, universal currency: energy. Kardashev's insight was elegant in its simplicity. Whatever a civilization looks like, wherever it exists, whatever it is made of, however it thinks it needs energy to function and grow, energy is the one quantity that scales directly with capability across any conceivable form of intelligence. You cannot build, compute, communicate, or expand without it. Energy consumption is therefore the most honest and universal measure of how far a civilization has actually developed. Not its philosophy, not its art, its what's. On this basis, Kardashev proposed three categories. A Type 1 civilization has achieved full mastery of its home planet's energy resources. It harvests every available form of planetary energy, solar, geothermal, tidal, atmospheric, with complete efficiency. It has moved entirely beyond dependence on stored fossil fuels. It can regulate its own climate and manage geological processes at a planetary scale. The total energy budget of a Type 1 civilization runs at approximately 10 to the power of 16 watts. A Type 2 civilization has moved beyond its planet entirely and harvests the full energy output of its parent star. The theoretical engineering solution most commonly discussed is the Dyson sphere, a structure not necessarily solid, but a swarm of energy-collecting platforms completely surrounding the star and capturing essentially all of its radiation. The energy budget of a Type 2 civilization is approximately 10 to the power of 26 watts. To put that gap in perspective, a Type 2 civilization commands 10 billion times more energy than a Type 1. The difference between a Type 1 and a Type 2 is not a step forward. It is a different category of existence. A Type 3 civilization operates at the scale of an entire galaxy. It harvests energy from hundreds of billions of stars. Its engineering projects are visible across intergalactic distances as anomalies in the infrared spectrum, excess heat radiated by structures that should not exist according to natural astrophysics alone. Its energy budget approximately 10 to the power of 36 watts. Where does humanity sit on this scale? Currently at roughly 0.73, not Type 1, not close to Type 1. Physicist Michio Kaku has estimated that on our current trajectory, humanity might reach Type 1 status in somewhere between 100 and 200 years, assuming we do not destroy ourselves first. That qualifier is not rhetorical decoration. It is a load-bearing part of the sentence. Here is where the humor arrives, and it is the kind that is funny precisely because it is accurate. When SETI researchers transmit signals into deep space, hoping that someone out there will hear us, the situation from the perspective of the Kardashev scale resembles a person standing in a dense forest at midnight holding a small flashlight, waving it upward in the hope of flagging down a commercial aircraft cruising at 10,000 meters. Is it technically possible that the pilot might notice? Sure. Is it a realistic communication strategy between parties operating at those respective scales of capability? Not particularly. We are 0.73 on a scale that goes to 3. We are, in cosmic terms, pre-industrial. The search for Type 3 civilizations has been conducted in earnest. Infrared surveys of the sky, including large-scale projects that have scanned hundreds of thousands of galaxies, have looked specifically for the thermal signatures that a galaxy-spanning engineering project would inevitably produce. When you enclose stars in energy-harvesting structures, the waste heat has to go somewhere. It radiates in the infrared. A Type 3 civilization managing an entire galaxy would be visible across the observable universe as a galaxy that is anomalously warm in ways that natural stellar physics cannot explain. The surveys have found no such anomalies of a convincing scale. One star generated significant attention. Tabby's star, formerly catalogued as KIC 84628552, was observed by the Kepler telescope to dim in irregular asymmetric patterns that no standard astrophysical model could cleanly explain. The dimming events were too large, too irregular, and too asymmetric to match the profile of an orbiting planet. For a period, the hypothesis of an incomplete Dyson sphere, a swarm of energy-harvesting structures still under construction around the star, was discussed seriously by credentialed astronomers in peer-reviewed contexts. The eventual consensus explanation settled on clouds of dust and cometary debris, but the fact that the artificial structure hypothesis was treated as scientifically legitimate rather than dismissed illustrates how seriously the field takes the possibility. There is a deeper implication that the Kardashev scale forces into focus. A Type 3 civilization is not simply a larger version of us. It operates with instruments and communicates through physics that we have not yet discovered. If they are transmitting signals, those signals may be passing through us constantly encoded in physical phenomena we do not yet have the conceptual framework to recognize. An ant colony has no mechanism for detecting Wi-Fi. The signal is present. The receiver does not exist yet. We may be in an equivalent position surrounded by communication we lack the physics to decode. The silence, in other words, may not be silence at all. It may be a conversation happening at a frequency we have not yet learned to hear. If a Type 3 civilization exists and is capable of perceiving us at all, do you think they would recognize what they are seeing as intelligence? There is one theory that proposes they not only recognize us, but that they are operating under a deliberate and explicit policy of silence toward civilizations like ours. And the reasoning behind that policy, once you follow it to its conclusion, will permanently change the way you see the night sky. The argument begins not with fear, but with logic. Cold, clean, unavoidable logic. Liu Cixin, the Chinese science fiction writer, articulated what is now called the dark forest theory as a solution to the Fermi paradox in his celebrated trilogy. But it is important to understand something from the outset. The theory does not depend on fiction to stand. Strip away every narrative element, every character, every dramatic device, and what remains is a chain of reasoning that holds together on pure logic alone. You do not have to enjoy science fiction to find it disturbing. You only have to follow the argument to its end. It begins with two premises. Neither is controversial. Neither requires any assumption beyond what basic physics and biology already tell us. The first premise: resources in any given region of space are finite. The universe is vast, beyond comprehension, but accessibility is constrained by the speed of light and the practicalities of distance. A civilization can only meaningfully exploit resources within a reachable sphere, and that sphere, however large, has boundaries. What exists within those boundaries does not expand indefinitely. Stars burn out. Matter is limited. Energy is not infinite within any practical region of space-time. The second premise: every civilization that survives long enough must expand. This is not a statement about greed or aggression. It is a statement about thermodynamics and biology. Any system that consumes energy and reproduces will eventually press against the limits of its local environment. Growth is not a cultural choice. It is a survival mechanism built into the logic of complex systems. A civilization that stops expanding eventually collapses inward when its local resources decline. This applies regardless of how peaceful, cooperative, or philosophically enlightened that civilization might be. These two premises taken together produce a problem. Two expanding civilizations in the same region of space are eventually in competition for the same finite pool of resources. This is not inevitable on a short timescale, but on the timescales of cosmic history, millions and billions of years. It becomes mathematically inescapable. Now, introduce what the theory calls the chain of suspicion. When one civilization detects another, it faces an information problem that cannot be solved. You cannot verify the intentions of an alien intelligence. You can receive their signals. You can decode their language. You can even believe genuinely and sincerely that they appear peaceful. But you cannot confirm that they will remain peaceful as they grow more powerful. You cannot know whether their values will drift. You cannot guarantee that future generations of their civilization will honor the commitments of the present ones. And here is the truly destabilizing part: they know you cannot verify this, which means they also cannot verify your intentions. Both parties are locked in mutual, unresolvable uncertainty about whether the other represents a future existential threat. This uncertainty is not a diplomatic problem that goodwill can dissolve. It is a structural feature of the situation. And when you layer technological asymmetry on top of it, the conclusion becomes very dark very quickly. Two civilizations that encounter each other are almost never at the same level of development. The universe is too old and development too variable for that kind of coincidence to be the norm. One party is almost always more advanced. The more advanced civilization faces a choice that is not from a purely logical standpoint difficult. If it allows the less advanced civilization to continue developing, that civilization may eventually become capable of posing a threat, and the window to prevent that threat will have closed. If it acts while the power differential is still decisive, it eliminates a potential threat at minimal cost. From the perspective of pure survival logic, not malice, not cruelty, not hatred, but the same cold calculus that governs any competitive system, the rational move is preemption. The conclusion that follows is not comfortable to state plainly, but it is the conclusion the logic produces. The safest strategy for any civilization that discovers another is to eliminate it before it can become dangerous. Not because they are evil, because they are rational, and the alternative, trusting an unverifiable promise from an entity whose future trajectory is unknown, carries asymmetric downside risk. If this logic holds even partially, the behavioral consequence for every civilization in the galaxy is the same. You hide. You erase your traces. You never broadcast your location. You treat the detection of another civilization not as an opportunity for contact, but as a threat, requiring immediate assessment and potentially lethal response. The universe becomes a dark forest in which every hunter moves in silence, every fire is dangerous, and the only safe rule is, do not let anyone know you are here. The terrifying elegance of this theory is that it predicts exactly what we observe. A galaxy that should be loud with signals is instead perfectly silent, not because it is empty, but because every civilization in it has independently arrived at the same conclusion. Silence is survival. Visibility is death. The forest is full of hunters who have all learned not to make a sound. The most common objection raised against the dark forest theory is that not every civilization would necessarily adopt this logic. Perhaps cooperative, communicative civilizations exist. Perhaps some species develop ethics that override the survival calculus. The counterargument is straightforward and brutal. You only need one. One civilization sufficiently advanced and sufficiently committed to the dark forest logic can eliminate every cooperative civilization it encounters. Over billions of years of cosmic history, one such predator civilization moving through the galaxy, systematically responding to any detected signal with termination, would be enough to silence the entire galaxy. The cooperative civilizations vanish. The ones that survive are the ones that learn to hide. What remains is a galaxy of creatures holding their breath in the dark. The theory does not require that most civilizations are predatory. It only requires that the most capable ones are, or that even peaceful civilizations eventually understand the game well enough to go quiet. And the data agrees. The prediction of the dark forest theory matches the observation exactly: total uniform galaxy-wide silence. If the dark forest is real, if that is the actual structure of the universe, we have been broadcasting radio signals for over 100 years and sent Voyager out with a map to our location. What does that mean for us? On that subject, we did not only broadcast radio, we have done considerably more than that, and some of it cannot be undone. There is no quiet way to say this. Humanity has been advertising its existence to the cosmos for over a century, without anyone making that decision deliberately, collectively, or with any serious consideration of the consequences. It started around 1920 when commercial radio broadcasting began in earnest. From that point forward, Earth has been leaking electromagnetic radiation into space continuously, a growing sphere of radio waves, television signals, military radar pulses, and satellite transmissions, expanding outward in every direction at the speed of light. That sphere currently has a diameter of somewhere between 200 and 210 light years. Every star system within that radius, and there are thousands of them, has already been reached by the leading edge of our electromagnetic signature. The signal weakens with distance following a precise physical law. Intensity drops with the square of the distance traveled. A signal that is perfectly clear at 1 light year becomes 100 times fainter at 10 light years, 10,000 times fainter at 100 light years. By the time our earliest radio broadcasts reach stars at the far edge of that bubble, they are extraordinarily faint, buried in the natural noise of the interstellar medium, difficult to extract even in principle. A civilization with technology comparable to ours would likely struggle to detect them at that range. A civilization more advanced than ours is a different matter entirely. A sufficiently capable receiver, the kind that a Type 2 or Type 3 civilization would operate routinely, could potentially filter our signals from the background noise even at those distances. We do not know the upper limit of what is technically achievable in signal recovery. We only know our own current limits, which are not the limits of physics. Then there is Voyager. Both Voyager 1 and Voyager 2 were launched in 1977 and have since travelled farther from Earth than any other human-made object in history. Voyager 1 crossed the boundary of the heliosphere, the bubble of solar wind that marks the edge of our Sun's direct influence, in 2012, making it the first human artifact to enter interstellar space. It is now more than 23 billion kilometers from Earth and still moving outward. Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to represent life and culture on Earth. Music from Bach, Chuck Berry, Indian classical ragas, and Azerbaijani folk songs. Spoken greetings in 55 languages. The sound of wind, rain, surf, and a human heartbeat. Images of human anatomy, architecture, food, and landscape. And critically, a pulsar map. The Golden Record's cover includes a diagram using the positions and frequencies of 14 pulsars, rapidly rotating neutron stars that emit electromagnetic pulses with extraordinary regularity as a coordinate system. Pulsars are essentially cosmic lighthouses with unique, measurable pulse rates, because each pulsar has a distinctive frequency that changes predictably over time. The map encodes not just a position, but a timestamp. Any civilization with knowledge of pulsar physics could use that map to locate our solar system with high precision. It is in effect a set of directions to Earth, etched into metal and thrown into the dark. Stephen Hawking, who spent considerable time thinking about the implications of contact with extraterrestrial intelligence, was direct about his assessment. He publicly compared the prospect of signaling our existence to the universe with the experience of indigenous peoples encountering colonial powers for the first time. An analogy that does not resolve in favor of the party doing the party, waving. Then there is METI, messaging extraterrestrial intelligence. Unlike SETI, which listens, METI transmits deliberately and intentionally towards specific targets. The Arecibo message sent in 1974 was a structured binary transmission beamed toward Messier 13, a globular cluster containing hundreds of thousands of stars, located approximately 25,000 light-years away. The message encoded information about human biology, our number system, the structure of DNA, and the position of Earth in the solar system. It was sent immediately after a ceremony celebrating the upgrade of the Arecibo telescope. There was no global consultation, no international debate, no democratic process of any kind. A group of scientists at a party decided to announce Earth's existence to a target 25,000 light-years away, and then went back to the reception. The humour in this, and it is real dark humour, of the most genuine kind, is that the most consequential transmission in the history of our species was essentially an afterthought at a celebration. If it turns out to have been a mistake, it will be the most cheerfully made mistake in recorded history. The scientific debate about intentional transmission became explicit and serious at a conference in San Jose in 2015, where researchers argued with unusual intensity about whether METI should continue. The group opposing further intentional transmissions included Stephen Hawking, Elon Musk, and a significant number of physicists and astronomers who signed a joint statement calling for a moratorium on active messaging until a global conversation could be held. Their argument was not that contact would definitely be dangerous. It was that even an extremely small probability of catastrophic outcome, 1 in a million, 1 in a billion, represents an unacceptable risk when the downside is civilizational destruction. The counter-argument from those supporting METI had its own logic. The electromagnetic bubble is already out there. If anyone within 200 light-years has the capability to detect and analyze our accidental transmissions, they already know we exist. The deliberate messages add marginal exposure to a situation that is already exposed. Silence now does not undo what has already been broadcast. Both arguments are coherent, both have merit, and neither resolves the underlying problem, which is that the decision has already been made not through deliberate choice, but through a century of technology development that nobody treated as a first contact protocol. The signals are traveling. The golden records are drifting through interstellar space. The map is out there. There is no version of events in which we get to decide again from the beginning. If you had a vote right now, knowing everything you know about the silence of the universe and the theories that try to explain it, would you support continuing to send signals outward, or would you go quiet and hope it is not already too late? Whether we want to face it or not, a larger question is, waiting one that repositions everything. Where does humanity actually stand in this story? Are we the next victim of a filter we cannot see, a target in a forest we did not know was dangerous, or something else entirely, something no one has quite dared to consider yet? The great filter is not an event. That is the first thing to understand clearly, because the name suggests something singular, a moment, a threshold, a specific catastrophe that either happens or does not. The reality is more unsettling. The Great Filter is a name for any step in the long chain from inert matter to spacefaring civilization, where the probability of crossing is so close to zero that across billions of years and hundreds of billions of worlds, almost nothing makes it through. It could be one step, it could be several. What makes it a filter is not its nature, but its effect. The universe on the other side of it is empty. To understand where the filter might sit, you first need to lay out the full chain of steps that any civilization must survive. It begins with a stable, rocky planet in a habitable zone. From there, the origin of simple life, prokaryotes, single-celled organisms without a nucleus. Then the jump to complex cells with a nucleus called eukaryotes. Then sexual reproduction, which dramatically accelerates the rate at which evolution can generate novelty. Then multicellular life. Then animals with central nervous systems and vertebral structures capable of supporting increasingly complex brains. Then language and tool use. Then industrial technology. Then the capability to reach space. And finally the step that no civilization we can observe has demonstrably cleared the ability to survive its own technological power long enough to become permanently multiplanetary. Every one of those steps is a candidate. The filter could be anywhere along that sequence. The silence of the universe tells us that at least one of them is nearly impassable. It does not tell us which one. The strongest candidate for a filter that lies behind us, one we have already crossed, is the transition from prokaryotic to eukaryotic cells. The timeline alone is striking. Prokaryotes, the simplest form of cellular life, appeared on Earth approximately 3.8 billion years ago. The first eukaryotic cells, cells with a true nucleus, membrane-bound organelles, and vastly greater complexity did not appear until approximately 1.8 to 2 billion years ago. That gap is 2 billion years. For 2 billion years, life on Earth did essentially nothing but make more bacteria. The planet was covered in microbial mats and went nowhere. When the transition finally happened, it happened exactly once in 4 billion years of biological history. A prokaryotic cell engulfed another prokaryotic cell, an act that normally ends in digestion, but instead of destroying it, the host and the engulfed organism formed a permanent symbiotic relationship. The internalized cell eventually became the mitochondrion, the energy-producing structure found in virtually every complex cell alive today. Every animal, every plant, every fungus on Earth traces its lineage back to that single event. One merger, one time in 4 billion years. The probability of that specific sequence of events occurring by chance is difficult to calculate and impossible to overstate. If that improbability is what makes the filter, then the galaxy may be full of planets covered in bacteria that never go anywhere, and we, having somehow crossed that threshold, are the anomaly, but the filter may not be behind us. And if it is not, then it is ahead, and the candidates in that direction are considerably harder to look at calmly. Since 1945, humanity has possessed for the first time in its entire history the practical ability to destroy its own civilization. The current global stockpile stands at more than 12,000 nuclear warheads. That number has declined from its Cold War peak, but the capability it represents has not diminished in any meaningful strategic sense. We have lived with this capacity for less than one human lifetime. We cannot point to any other civilization that has navigated this threshold successfully, because we have no examples of any other civilization at all. Artificial general intelligence represents a different category of risk, one without historical precedent in any domain of biology or technology. Unlike nuclear weapons, which are instruments that require human decisions to deploy a sufficiently capable artificial intelligence operating with misaligned objectives could pursue outcomes incompatible with human survival without any single human deciding to initiate that process. The timeline for when this risk becomes acute is genuinely uncertain. The direction of development is not. Synthetic biology adds a third dimension. The tools required to design and produce novel biological agents are becoming less expensive and more accessible with each passing year. The gap between what a well-funded state program can do and what a small, determined group of individuals could eventually accomplish is narrowing. An engineered pathogen optimized for transmissibility and lethality represents a risk profile that natural selection has never produced and that our immune systems and public health infrastructure were not designed to handle. Climate disruption occupies a different category, less likely to produce outright extinction, more likely to unravel the complex interdependent systems that industrial civilization requires to function. A world that has been pushed into sustained crisis by ecological collapse is a world that cannot maintain the research infrastructure, the international cooperation, or the economic surplus necessary to develop and deploy space technology at meaningful scale. What makes the current moment genuinely singular is that all four of these thresholds are active simultaneously, not spread across centuries, but compressed into a single 100-year window. The same century that produced nuclear weapons is producing artificial intelligence, synthetic biology, and measurable planetary-scale ecological change. No previous generation has faced the full set at once. The silence of the universe offers no comfort on this point. If advanced civilizations routinely crossed the transition to complex life, to intelligence, to industrial technology, and then consistently went quiet before reaching the stars, then the filter is precisely where we are standing. The data would look exactly as it does, a universe where life exists, but where something stops it from persisting long enough to fill the galaxy. The cosmic silence is not just a mystery, it is a data point, and it is pointing directly at us. Do you believe humanity will navigate the next 200 years without a civilization-ending event? The answer to that question carries implications that extend far beyond our own survival, because there is a reading of this situation, a different interpretation of the exact same data that changes everything about what this moment means. And it begins with a possibility almost no one seriously considers. Everything said so far has been scientifically accurate. The Fermi paradox is real. The Great Filter is a legitimate framework supported by genuine logic. The dark forest, while not proven, is consistent with every observation. The risks ahead of us are not exaggerated, but there is another way to read the same data. Not a more comfortable reading, a more precise one. And it inverts almost everything. Start from the beginning, but approach it from a different direction. The universe is 13.8 billion years old. But the conditions necessary for the kind of planet that can support complex life did not exist from the beginning. The first generation of stars that formed after the Big Bang were composed almost entirely of hydrogen and helium, the only elements that existed in significant quantities at that time. They contained almost none of the heavier elements that rocky planets, biological chemistry, and complex life require. Carbon, oxygen, iron, phosphorus, calcium. These are manufactured inside stars through nuclear fusion and scattered into space only when those stars die, sometimes explosively, as supernovae. This means the raw materials for complex planetary systems had to be assembled across multiple stellar generations. A star forms, burns for millions or billions of years, dies and distributes its heavy elements into the surrounding nebula. Those elements then contribute to the next generation of stars and their planetary systems, which are now richer in the building blocks of chemistry. Complex life on this timeline becomes chemically possible only after sufficient generations of stellar birth and death have enriched the interstellar medium. The implication is that the window for complex life in this universe has not been open for 13.8 billion years. It has been open for at most 5 to 10 billion years, and meaningfully open for considerably less than that in many regions of the galaxy. Our own solar system formed approximately 4.5 billion years ago, relatively early in the period when the conditions for complex planetary chemistry were becoming available at scale. This places us in an unexpected position. We have spent this entire story asking why no one arrived before us. But the premise embedded in that question, that we are late, that the galaxy had billions of years to fill up before we appeared, may be wrong. We may not be late at all. We may be among the first. The humour in this realization is genuine and slightly absurd. After all the existential weight of the Fermi paradox, all the dread of filters and dark forests and cosmic silence, one possible answer is the simplest one. Nobody else is home yet, because the universe has only recently finished building the conditions for anyone to be home. We are not the student who arrived last and found the seats taken. We may be the teacher who showed up before the students exist. This reframing does not dissolve the danger. The great filter could still be ahead of us. The dark forest could still be real, but it changes the meaning of the silence in a fundamental way. If we are among the earliest civilizations in this region of the cosmos to reach technological capability, then the silence is not evidence of universal failure. It is simply the quiet of a universe that has not yet had time to become loud. And if that is true, what follows from it is not comforting in a soft way. It is something more demanding than comfort. If humanity survives, if we cross the thresholds that have apparently stopped everything else, if we develop the wisdom to match our power, if we extend our presence beyond this single fragile world, we would not be joining a community of galactic civilizations. We would be in all likelihood among its founders. The decisions made by this species in this century about how to organize itself, how to use its technology, and whether to persist those decisions may echo across billions of years and hundreds of billions of future worlds. Not because we are special by nature, because we happen to be here now, at this moment in this window. Carl Sagan said that we are a way for the cosmos to know itself. This is not poetry. Every atom in a human body was forged in the nuclear furnace of a dying star. The carbon in your cells was synthesized billions of years ago in a stellar core and scattered through space before eventually becoming part of a planet, a biosphere, and finally, a nervous system capable of asking questions about its own origin. When a human being looks up at the night sky and wonders what is out there that is in the most literal physical sense, the universe turning its attention back on itself for the first time in this region of space. That is not a figure of speech. It is a description of what is actually happening. The responsibility that flows from this is not assigned by anyone. There is no cosmic authority that has designated humanity as the custodian of this corner of the galaxy. The responsibility arises from something simpler and more absolute. We may be the only ones here who can carry it. If that is even partially true, then everything that happens on this planet in the coming centuries is not merely our concern. It is the concern of everything that could come after us, every civilization that might eventually arise, every form of intelligence that might someday fill the silence if we manage not to end the story here. The silence is not a verdict. It is an open question, and it is addressed whether we chose to accept it or not directly to us. If we are genuinely among the first civilizations to reach this point, does that change how you see what is happening on Earth right now? The final question is not what the silence means. We have followed that question as far as it goes. The final question is what we do with it, and the answer to that is not being written in the stars. It is being written here now by the generation that happens to be alive at this particular and possibly unrepeatable moment. We began with a contradiction, not a philosophical puzzle, not a poetic metaphor, but a genuine mathematical contradiction, the kind that sits in the middle of a table and refuses to be moved. A universe 13.8 billion years old, hundreds of billions of stars, more planets than grains of sand on every beach on Earth, billions of years of cosmic time during which intelligence could have risen, spread, and filled the galaxy many times over. And against all of that, perfect, total, unbroken silence. That was where this story started. With the gap between what the numbers demand and what reality delivers. From there, we followed the logic wherever it led, without softening the destinations. We learned that the silence is not a gap in our data, it is the data itself. 60 years of continuous, methodical, increasingly sensitive listening have returned nothing that survives scrutiny. The absence is not provisional, waiting to be overturned by a better telescope pointed at the right frequency. It is consistent, uniform, and total across every instrument and every method we have ever deployed. We confronted the explanations, each of which was frightening in its own distinct way. Perhaps Earth is not a typical world, but an extraordinary accident, a collision of rare circumstances, a moon of improbable size, a planetary shield in exactly the right orbit, a magnetic field generated by an unlikely liquid core, all converging on the same world at the same time. Perhaps we are not the rule, but the exception so extreme it is effectively unique. Perhaps the filter that stopped everything else is already behind us. Buried somewhere in the 2 billion years, it took a single cell to swallow another cell and not digest it. Perhaps against all the odds that compounded every step we got through. Or perhaps the filter is ahead. Perhaps every civilization that reaches the point of technological capability, the point we have already reached, the point we are currently navigating, hits a wall it cannot cross. Perhaps the silence is not the silence of empty space, but the silence of civilizations that one by one extinguish themselves in the window between gaining the power to destroy and developing the wisdom not to. Perhaps that window is simply too narrow for anything to survive it. And perhaps the fact that we have already built more than 12,000 nuclear warheads, are actively developing artificial general intelligence, and are acquiring the capability to engineer novel biological agents all within the same century is not a coincidence, but a pattern. The same pattern repeating with the same result. Or perhaps the forest is dark and full. Perhaps the silence is not empty, but populated by civilizations so experienced in the logic of survival that they have learned the one rule that matters above all others: do not make a sound. Perhaps our century of radio broadcasts and our golden records drifting through interstellar space have already been noticed by something that is now quietly deciding what to do about us. Or perhaps we arrived early to a party that has not yet started. Perhaps the universe has only recently finished constructing the conditions under which complex life becomes chemically possible at scale, and we are among the first rather than the forgotten. Perhaps the silence is not a graveyard, but a blank page, the quiet that precedes a story rather than the quiet that follows one. Every one of these possibilities is consistent with the available evidence. None of them can be ruled out. And this is the honest thing that must be said clearly without softening nobody knows. Not the physicists, not the astrobiologists, not the SETI researchers who have devoted their careers to the question. The universe has not told us which of these scenarios is real. The silence, for all the things it implies, does not specify its own cause. What we do know is that the question is no longer purely theoretical. Right now, the James Webb Space Telescope is analysing the atmospheric chemistry of planets orbiting distant stars. searching for the specific combination of gases, oxygen, methane, carbon dioxide, in particular ratios that on Earth is produced by biological processes, and essentially nothing else. This is the first time in human history that our technology has been capable of doing this. We are not guessing at whether life exists elsewhere. We are reading the chemical fingerprints of other worlds' atmospheres from 100 light-years away, looking for the signature of something alive. The results of that search, accumulating year by year, will shift the probability distribution of every framework discussed in this story. At the same time, Europa Clipper is traveling toward Jupiter's moon, carrying instruments designed to characterize an ocean that has existed in darkness for billions of years. Whatever it finds or does not find in that ocean will reposition our understanding of where the Great Filter sits with a precision that no amount of theoretical argument can match. A positive result changes everything in one direction. A negative result changes everything in another. Either way, the answer is coming. And while those instruments travel and observe, humanity is simultaneously pressing forward on artificial intelligence, synthetic biology, and planetary-scale environmental systems, not as separate trajectories with separate timelines, but as converging pressures arriving together within a single human lifetime, without the benefit of any prior example of how to navigate them successfully. We are at this moment both the civilization asking whether anyone else made it through, and the civilization in the process of finding out whether we will. The generation alive today is not the generation that will know the final answer to the Fermi paradox. The signals traveling outward from Earth will not return answers for centuries or millennia, if ever. The James Webb Telescope will build its catalogue of atmospheric data over decades. Europa Clipper will reach its destination years from now. The long arc of this question bends far beyond any single human lifetime. But the generation alive today is the generation that will determine which direction that arc bends, not through a single decision, not through a single discovery, but through the accumulated weight of choices made in this century about how to manage the technologies that define the filter threshold. The physics does not care about our intentions. The logic of the Great Filter does not grant exceptions for good reasons or noble ambitions. The only variable it measures is outcome. The universe is 13.8 billion years old. It has been silent for every one of those years that we have been capable of listening. We are here by luck, by probability, by whatever word fits the chain of near impossibilities that produced a planet, a biosphere, a nervous system, and a species that eventually looked up and started asking questions. The story is not finished. There is no ending written yet. What comes next depends entirely on what happens over the next few hundred years on a small planet orbiting an unremarkable star on the outer edge of an average galaxy in a universe that has offered no guidance, no warning, and no answer. Only silence. And the silence, as we have learned, means everything or nothing. We are the ones who will find out which. One last question after everything. Do you want the universe to answer, or do you want us to be the ones left to write the ending?